So welcome to today's session. I'm Roshani. I'm a Microsoft Student Ambassador, and today I'm going to be having a session on an introduction to quantum computing and the Azure Quantum Development Kit. So let's get right into it. So this is a brief introduction to me, Roshni. I'm a student ambassador for Microsoft. My LinkedIn profile is right there if you want to check it out. And my expertise lie in quantum computing, Qiskit, quantum machine learning, AI, and ML. And you can check out the rest of it right there. We're going to move on to the next slides. Today's agenda. What are we doing today and what's the purpose of this session? Okay, so what is today's agenda? We're gonna first cover what is quantum computing. I'm gonna tell you about how quantum computers are different from classical computers. We're also going to get into the history of quantum computers and how it all began and where we're at right now. Other than that, we're also going to look into the architecture of a quantum computer. From there on, we're going to get into my favorite part, which is the applications of a quantum computer. Where necessarily can we use quantum computers in places where we can't use classical computers? We're going to get into that shortly. And we're going to compare it with classical computers, after which we're going to get into how you can learn quantum computing. We're going to discuss some popular languages which you can use for writing quantum algorithms, after which we're going to look into the impact that quantum computing has on the real world. We're also going to discuss why right now specifically is a good time for you to start your journey with quantum computing. Lastly, we're going to discuss the quantum development kit. So I hope you're ready to get into this. What is quantum computing? To give you a bit of a overview, kind of like from the fundamentals of what quantum computing is. So you must know that a regular digital computer works with binary digits, binary bits, zeros and ones. So everything, your input, the output, it's all converted into binary bits. And these binary bits are how information is processed in a regular classical computer, which would be your phone, your tablet, computer, you name it. It's a classical computer. From your phone to the best supercomputer that we have, all of these operate on zeros and ones. But what makes a quantum computer so different from these regular computers that we're so accustomed to? It's that they don't work on zeros and ones. They actually use the laws of quantum mechanics to work with something much cooler called a qubit or a quantum bit. So you must be thinking, okay, that's a really cool name, but how is a quantum bit different from what we're accustomed to? Well, you see, for this, we need to look a bit back into the foundations of theoretical physics and where it really came from. So quantum bits can exist in what we call superposition. What is superposition? Well, it's really simple. The bit can exist, the qubit, not the bit, the qubit can exist in both a 0 and a 1, or really anything in between. It can exist in infinite different states, and that is because of superposition. To give you an idea of what superposition is, there's actually a really good experiment. It's called Schrodinger's cat. I'm not sure if you know about that, but I'm just going to go over that for a second. There was a physicist named Erwin Schrödinger, and he had this experiment which he performed. Now, we don't actually know the exact details of it, but what happens is he takes a cat, he places the cat into a cardboard box, and then he places a vial of poison inside the cardboard box. Now, you don't actually know if it's a cardboard vial of poison or whatever, but anything that could pose lethal harm to the cat. And he places it, and then he closes the lid of the box. Now, from an observer's standpoint, what do you think is happening? The cat could be dead, the cat could be alive, or the cat could be, well, taking a nap. You don't know that. You don't know it for certain unless you open the box. and that is superposition. Superposition is the state of everything happening simultaneously at the same time. So if we're going to look at this situation, the cat can be both dead and alive and anything in between. And that is different universes in themselves. One universe in which the cat is alive, another universe in which the cat is not so alive. So coming back to quantum computing and qubits and how we use that. So you'll realize that using the law of superposition, we can maintain the state of a 0 and a 1 and everything simultaneously at the same time. So this enables something called parallelism. Parallelism is basically what I mentioned to you right now, how when you close the cardboard box, there's many different realities that can emerge as a result of that, where in one universe, the cat's alive and so on and so on. You get the point. That is parallelism. And I'm going to get into why that is computationally so important to understand so many things that happen in nature, or whether that's in science and optimization. We're going to get into that today. So moving to the next slide, I'm just going to have some water. Okay. So the development of quantum computing, well, it all started with theoretical physics. So back in the 1980s, we had physicists like Richard Feynman and Max Planck, who laid the foundation for what we know now as quantum computing. But you see, the thing is, back then, when and they were discovering these new things, they didn't actually have the hardware. I mean, if you think about it, we didn't even have proper classical computers back then. Computers were the size of rooms. If you remember those images that you've seen, it would take so many rooms and those vacuum tubes, and it was quite impractical. But that is where our journey of quantum computing begins. After which we come to the 1990s, where you have a really cool algorithm called Shor's algorithm. This is very important. And the reason why it's very important is because what Shor's algorithm is it's an algorithm that allows you to find the prime factors of really large numbers. Now, you want to keep that in mind because we're going to come back to that later, and it has something to do with data encryption. We're going to get into that soon enough. Now we have the 2000s, where you have, well, early computers and quantum computers which start emerging, and people start getting more interested in it. Now it's not just theoretical physics. Now it's also computing and engineering, so many different fields put together into one awesome field called quantum computing. And then you move into the 2010s. Now, one of the first, I would not the first, but one of the most major advancements that we had in this field was in 2019 when Google unveiled the Sycamore chip, the quantum chip. And that was the first time that we discovered that quantum supremacy is real. And now when I say quantum supremacy, I don't want you to assume that a quantum computer is going to be better at every task that your general normal classical computer does. That's not true, but there are certain tasks which it can do infinitely faster. And so getting more into that now, well, I want to say a few weeks ago, Google unveiled the new quantum chip called Willow, and it's shown significant improvements in a reduction of error rate and speed. We're going to get more into that. So let's continue. Let's get into quantum computing architecture. So if you look very carefully right here at this image, this huge pipe-like structure, that is a quantum computer. So the reason why we keep it this way is actually because you're working with atoms, right? Qubits perform computations on an atomic level. So something that atoms are a subject to is decoherence. What is decoherence? Well, it's when a qubit collapses into a regular binary bit. So to explain it really simply, the qubit forgets that it's a quantum bit it becomes a classical bit. And we don't want that, obviously, because we already have classical computers to do that. So we keep it in this huge metal structure, which is actually a cryogenic environment. Cryogenic means it's really, really cold. Quantum computers are kept at a temperature of minus 15 millikelvin, which is also the coldest temperature known in the universe. So I think that gives you an idea of the architecture outside. But if we're going more in depth into the structure of how it works, it's really similar to a classical computer. The only difference is that in a classical computer, you have bits. The very fundamental of a computer is zeros and ones. It's bits. And those bits over here, instead of being zeros and ones, are qubits. Now, those qubits form quantum gates. So in a classical computer, you have gates like AND gate, OR gate, NOT gate. Over here, instead, you have gates like the Hadamard gate, really fancy name. And now these gates put together form a quantum circuit. These circuits put together form quantum hardware, which is kept inside that structure right there. I hope that gives you an idea of the hardware, the structure of a quantum computer, so you can visualize it a bit better. The applications of quantum computing. This, in my opinion, is the most important part of this presentation and really showcases where and why we need quantum computers. First of all, discussing cryptography. I had told you to remember Shor's algorithm, right? Shor's algorithm helps you find the prime factors of really, really large numbers. Now, you have certain methods of cryptography that we use, like RSA, for example, which, well, the whole purpose of them is that you have really large numbers and you can't find the prime factors of these large numbers. And that is what prevents your data from being stolen because it encrypts your data. So in encryption, you've got your encrypted data and you've got your key. So the key is basically just the prime factors of, imagine like an enormous number. So what quantum computers do is that it's actually really, really easy to break that. And the reason for that is because you have something called parallelism, which I had mentioned before, where you have multiple universes, right? Now, what does that mean? It means that while your classical computer, now see, the thing about Shor's algorithm is you can run Shor's algorithm on a classical computer and a quantum computer as well. But if you were to run it on a classical computer, because of the sequential nature of classical computers, where it's going to test every possible option. And by the time it finishes testing the options and actually finds the key to your encrypted data, it's going to be 20,000 years in the future, and you and your entire bloodline has gone extinct. So, really, that's not possible. So, the thing about encrypted data is that it's not that it can't be decrypted. It can. It most definitely can. It just takes a very long time. But that's not true with quantum computers because um, because of the fact that you have parallelism and you can basically just go in with all of these possibilities at the same time using the power of, as I've said it for the millionth time, parallelism. So yeah, I think that gives you an idea of how quantum computers can destroy the current structure of cryptography, but also create better systems in cryptography. Now we're going to focus on optimization, which is next. So I've mentioned finance and logistics over here. There's obviously a lot more ways in which you can, a lot more scenarios in which you can optimize, but just a second. Yes, okay. So my presentation, a minute, please. There we go. Yes. So I want you to think of an example, right? An example, a very simple example of helping you understand what I mean when I say that this helps with optimization. It's that imagine you work at Amazon, right? And you've got a package and you want to deliver this package to a random customer, right? So you've got imagine there's 5 different paths you can choose from to deliver this package to said customer. So you consider a couple of constraints. What are those constraints? Time, how much money you're willing to put into it, and well, the terrain. Somebody was unmuted. Okay, never mind. Please, it would be great if you could all stay muted. It's a little distracting. Okay, so moving back to the Amazon example, if you have 5 different paths to pick from and a certain amount of constraints, obviously you're going to mathematically or computationally try to figure out which path is the best. Now, generally, the way that this is done in classical computing is sequentially. So you're going to check, okay, this path, I'm going to go through this path. No, that one's not great. This one, not so great either. And then so on and so forth until you find the right path. But you see, the issue is that in real life scenarios, you don't have um, in real life scenarios, you don't have just one path or no, just 5 paths and just one customer or something like that. I mean, in real life scenario, you would have millions of customers and the entire earth as your map. Now, how are you going to work with that? How are you going to work on such a large scale? Well, using classical computing, it takes a lot of time, a lot of resources, and we don't like that. So instead, you can use the parallel processing power of a quantum computer and perform all of these permutations and combinations simultaneously at the same time. I hope that gives you an idea of how this helps, because it drastically reduces the amount of computation that you have to perform, which also reduces the amount of time that you're spending on these. Moving on to material science, simulating molecular structures and chemical reactions. Now, I've mentioned cryptography and optimization, so it's a very random thought to think, okay, how can we use quantum computers in chemical reactions? That's weird, but I would like you to take a moment and think. A quantum computer is quantum in nature, but what else is quantum in nature? Molecules. Yeah. So because of the fact that chemicals, molecular structures, and quantum computers are governed by the same laws of quantum mechanics, it makes simulating things like, for example, simulating photosynthesis so much easier. I was actually reading into it a while back. Simulating something as simple, I mean, I shouldn't call it simple, but because, okay, so simulating something as basic as photosynthesis can be quite computationally exhaustive if done on a classical computer. Why? Because it takes so much time. There's a lot of complex math involved in it, which is inherently quantum in nature. So to be able to do these computations on a classical computer, frankly, is impractical. But we had no other technology up till this point. But now that we have quantum computers, to be able to simulate things such as photosynthesis or proteins and so many different things in healthcare and medicine is far more effective, and frankly it really opens new horizons of what can be done in the field of healthcare and medicine, new drug discovery as well. Other than that, we also have machine learning. So machine learning, I want to give like a bit of a personal experience with this one. So this summer I had a project I made, which was a Spotify music recommendation algorithm using quantum machine learning. So, see, the thing about regular machine learning is that when you're obviously you work with a huge amount of data, and whenever you're processing this data, even with supercomputer access, which I did have, it can end up taking anywhere from 5 to 8 hours just to process this data. So you can imagine how absolutely annoying it is to do it on a massive scale. But again, because of the fact that we can do this parallelly using a quantum computer, it doesn't take that much time. And you also have specific algorithms like Grover's search algorithm, which make the process far more accurate, efficient, and the results are much better than what you would get on classical computing. The only downside is that while all of this sounds really good and amazing, we don't have the hardware for that yet. However, I don't want you to be discouraged because from the trajectory that we've seen so far, quantum computing is a drastically developing field. Just because we don't have the technology for it today doesn't mean we won't have it like 2 years in the future. Moving on to the next slide. So this is a bit of a recap of what we've done so far and comparing classical computers and quantum computers. So as I've gone over this before, classical computers work with bits, binary bits, which is zeros and ones, whereas quantum computers work with qubits, which exist in superposition, so 0, 1, everything in between. Parallelism, again, classical computers operate in a sequential manner, going through every single option manually one by one, whereas quantum computers do all of these operations at the same time, saving a lot of time. Now, entanglement, I didn't really go over entanglement much, but I will tell you what it is now. So if you're not familiar with what entanglement is, I want you to think of a very basic example, which will help you clear this up. So imagine I have two boxes, right? One of the boxes has a hot dog in it, and the other box has a burger in it, right? So, if I ask you, which one of these boxes has a hot dog in it? How are you gonna tell me? You have no idea. It could be any one of those boxes. That's an absurd question. It is an absurd question until you open one of the boxes. Now imagine you open the box and you see, there's a hot dog in this. So the other box must have a burger in it, right? Because that's the only option that exists. This is a very basic example of what entanglement is. See, because the state of one box affects the state of the other box, there was a hot dog in one box. That's why I know and you know that there was a burger in the other box. That's simple. But when you think about it in the quantum mechanical state and the way that we work with qubits, it's that the state of one atom affects the state of another atom. And this is what helps us work with parallelism, entanglement, and so many other quantum mechanical terms and ideas put together into a computer. Applications, I believe I covered cryptography and optimization. I think that's pretty clear by now. So let's move on to the next slide. So now that I've got you hopefully excited about this field, let's get into how you can learn quantum computing. So there's definitely like a couple of things you need to know beforehand. And the first would be you need to have a good understanding of linear algebra. Why? Because, well, see, the state of qubits is represented through vectors in a complex vector space. And gates, like I mentioned before, Hadamard gate, are represented as matrices. So if you have a good idea of linear algebra, you're not going to be so lost in quantum computing. After which you need to know the basics of quantum mechanics. Now, please don't freak out when I say that, but the basics of quantum mechanics, really terms like entanglement, superposition, allow you to build your own quantum circuit and work and run your own algorithms on a quantum computer. After which you have classical computing. Now, I would say it's really good if you have a good idea of Python and are familiar with how to navigate through Python libraries. As long as you know that much, or you are willing to learn that much, you're good to go. It's great. And quantum programming. So what you do in quantum programming is you actually build quantum circuits, and then you place those in your quantum algorithms. And the third step over here is actually you take whatever quantum algorithm you've created and you run it on quantum simulators, which are provided to you by Qiskit, IBM Quantum, and also Azure services. So let's move on. some popular quantum programming languages. So I did mention before that you have to have a good understanding of Python because that's very beneficial. Because if you know how to work with Python, there are different libraries that you can work with. Like for example, you have Circ. Circ is by Google and it's a quantum computing framework. You've also got other libraries and you have different languages as well, like Qiskit, which is by IBM. You've also got Q Sharp, which is like C Sharp, but quantum, and it's obviously by Microsoft, and you can use this along with the Quantum Development Kit. You've also got Ocean, which is by D-Wave, and you've got QMod, PennyLane. There's a link provided right here, which you can check out if you want to. I'm also going to be, by the way, I'm going to be providing this presentation in the chat after the session is done. So if you don't check it out right now, don't worry about it. You can check it out after the session is done, but I've added the link right there. And the impact of quantum computing on the computing world. Again, this is a little bit of a recap. I'm trying to go slow in case there are people who are new to this concept. So cryptography, you can use Shor's algorithm, parallelism to be able to break old encryption systems and build more secure ones. And you've got drug discovery, where you can obviously recreate molecular interactions. You can simulate nature in ways that we have never been able to with classical computers. Financial services, this is where you would use optimization, where you would analyze risk, or you would optimize portfolios in finance. And artificial intelligence and quantum machine learning, obviously, here, instead of spending 7 hours for your data processing, you can spend much less and you can actually get your algorithm running more efficiently, more accurately as well. Why should you learn quantum computing right now? So you see, the awesome thing is that while the idea for quantum computing came about a while back, I want to say like 50, 60 years back, we haven't had the hardware for that up till recently. And frankly, we don't have the imagined amazing cyberpunk science fiction hardware as of yet. But we will someday, which obviously means that this is a developing field, which gives you an opportunity to really explore. Because you see, the reality of the situation is that companies like IBM, Microsoft, and Google, they're investing so much into quantum supremacy. Like, for example, Google's recent quantum chip called Willow. These are amazing, fascinating, and they're leading us to a new future, like, you know, the kind that you see in movies. But at the same time, we don't have that many professionals in the quantum computing field. Like, oh my goodness, something happened. Just a second. Can you guys still see my presentation? Because, okay. I hope you can see my presentation. Can someone drop a message in the chat, please, letting me know if you can see it?
Yes, you can see it.
Okay, thank you so much. Okay, cool. So where was I? Yeah, so despite the fact that companies like IBM, Microsoft, and Google are investing so much into this field, we don't have nearly that many experts in this field as compared to, you know, software engineering or others. And that's why it's a really good time for you to get into it, because frankly, it's not that competitive yet, but trust me, it will be. With the way that it's been growing, the potential that it's been showing, I would like to let you know that after Google launched their Willow quantum chip, their share prices have been at an all-time high. So it's not just scientists and physicists who see it, it's also investors who are starting to see the potential that quantum computing holds, which is why it makes this the perfect time for you to really get into the field and have kind of an early advantage that other people won't. Other than that, it's also an interdisciplinary field, which means that obviously you're going to be combining physics, computer science, engineering, physics, because obviously you're working with laws of quantum mechanics, you're working with qubits, your operations, computations are all done on an atomic level. Computer science, because you actually need to know how to program these. and engineering because you're working with hardware, wires, so many cool things put together. And lastly, I wrote future-proof skills because, every day you go on YouTube and there's one or the other video talking about how ChatGPT is going to take over your job. Well, chances are, yes, it will if you can't keep up with the dynamic landscape that you're in. And being a part of this proves that you're ahead of everybody else and you're evolving and you're adapting because that's what humans are meant to do. And if you can put yourself ahead of everybody else, then that makes sure that you are not going to be irrelevant in the market and in the job landscape. I hope that was a good enough idea. Now let's move on to the quantum development kit. So here, this is basically kind of a course that you can participate in. I'm gonna give you more information on this, but here you're gonna learn how to create a Q-Sharp program using the Azure Quantum Development Kit. You're also going to learn how Q-Sharp programs are structured. You're going to learn the basic structure, how to create a Q-Sharp file, define the logic of a problem, kind of like how you do in like the first computer science class that you have in school. And then you're going to combine classical and quantum operations to solve a problem, as in you're going to be taking a hybrid approach, and you're going to work with qubits and quantum operations to build a quantum random number generator. Some of the things that you need to know before getting into this is that you want to have a basic understanding of quantum computing concepts, which if you were listening to anything I said in this session, I'm pretty sure that you already passed that one. And second is you need to have basic knowledge of classical programming, such as Python. The rest is right there. Moving on to the next slide. So I do want to mention that, okay, you can build basic quantum programs using the Quantum Development Kit and Q-Sharp. And because generally the Azure Quantum Cloud Service is a paid service, if you use this link right here, you get $500 free, and you can actually use the Azure Quantum Cloud to run your quantum algorithms using Q-Sharp as a part of this course. And you're gonna adapt and create Q-Sharp applications, run them on actual hardware, and by that I mean actual hardware which you're going to be provided using the Azure Quantum Cloud Service, free of cost. And then again, I've mentioned once again, just so in case you come back to this later and you forget, it is free of cost. It's an open source software development kit, which can allow you to write quantum programs. And you're going to be using Q Sharp, which is a high level quantum programming language, which was developed by Microsoft. And these are some links that I've added because I will be sharing this presentation after my presentation. So this is going to take you around 3 hours and 24 minutes to complete. You're going to get 6 badges and a trophy and a certificate. These are all the links. You can check them out. I feel like when I started out with quantum computing, really the only thing I had was like YouTube videos by Michio Kaku and a couple of different sources to really understand what was going on. But in the past 1 year, we've really progressed so much, and there's so many more courses on quantum computing that you can check out. And this is a really, really good place to start if you want to understand what's going on from the very fundamental beginning. So yeah, do check those out. And this is an example of what your Microsoft Learn profile will look like, because to access the links that I've given over here, you actually need to have a Microsoft Learn profile. Again, it's free of cost. You don't need to panic about that. And you can click right here to create a Microsoft Learn profile if you don't already have one. If you do, then you can go right into the course. And this is the page where you will get your certifications, your badges, your trophies, and everything. You can also share it on LinkedIn. This is an example of what your certificate will look like. This one has my name on it, but yours will obviously have your name on it. And there's a link right here that you can access to check out this course specifically if you want to. And this is another example of what a sample certificate looks like. You can check that out. Once again, the link is given right there. You can click on that. And lastly, for today's event, this is what your certificate will look like. It's going to have your name right there. It's going to have my name right there, and it's going to have the event's name. And thanks for joining. That's it for my presentation. I hope you liked it, and I hope you learned something new. I hope it inspired you, and I really hope that if you're not in this field or if you're new to it, you keep going at it. And it's so amazing. It's a developing field. There's so much potential for everyone, and I can't wait to see more faces in this beautiful community. And this is the part where you guys ask me questions if you have any. Yeah, go ahead. Does anyone have any questions?
Yeah.
Uh,
Could I ask a question?
Yeah, of course, go ahead.
Oh, so my question is like about industrial right now. Like, what are you thinking in the quantum industrial? Like in the China, in the Russia, in the European, like that.
Um, could you please specify what necessarily you want me to talk
Like
about? Are
in
you
the future, like in your expect, because right now we are in the AI era, right? And like
Yeah.
everyone is using like ChatGPTs, AI chatbot, like that. So yeah, what's going on with the quantum technologies for the this industry?
I would actually say, I think a couple of months back, I had actually seen a video of a couple of people discussing where they see AI and quantum going, and somebody had said that artificial intelligence and quantum computing are fundamentally different. And back then, when I heard that, I thought, yeah, that makes sense. But the way that technology has been progressing, I think that after creating a couple of projects of my own, while intelligence and machine learning are I mean, awesome and different compared to anything we've had in the past, everything reaches its peak at one point. And that peak is classical computing. There is only so far that you can go with classical computing's capability, even when it comes to artificial intelligence. Because, I mean, like I said before, for a basic project, it ends up taking you 7 to 8 hours just to process your data. But you can do that much faster using a quantum computer. So you can just imagine the progress that that can bring along. And I also want to mention, since you asked, quantum computing is not necessarily just going to be for artificial intelligence, but also in fields that we haven't considered before, like, for example, treating illnesses, because of the fact that, again, they work on a quantum, I mean, they're governed by the same quantum laws. What happens is that there's so many things in nature that we don't understand. We don't understand it because we're going about it the wrong way. It's like, kind of like going to an island on a bike. You can't do that. And in that case, an island, I mean, in this case, the island is the mathematical research and biological things that we're trying to develop, and the bike in the water would be your classical computer. It's simply not possible to do that. And that's where quantum computers come in, where even though we don't have the hardware for it right now, it definitely creates a new kind of a new horizon for you to explore mathematically and understand the universe or medicine and so many different things that are not comprehensible with classical computing in a better fashion. So I hope that answers your question.
Okay, thank you very
Yeah,
much.
thank you. Are there any other questions? Are there any questions? Okay, if there's
so,
no question,
yes.
okay, there. Okay, yes,
So,
please.
what are you currently working on this basically in quantum computing research or?
Well, I'm currently a second year Bachelor's of Computer Application student, and I'm myself trying to figure out the quantum field better. I've attended a couple of events, met a couple of people who are more involved in the field, and I think my current goal as of now is to figure out how we can use quantum technology to work in fields of finance. And that's really been my primary goal because while I was invested in machine learning, I feel like somewhere I've come to realize that there's so much more potential to be had with quantum computing. And it's so much more intellectually satisfying because you're not just in the computing field, you're also so heavily involved with physics. And it gives you, like, when you work with a group of people who come from all different backgrounds, it gives you a sense of, okay, I really understand what's going on. And that's really what I'm focusing on right now. I'm trying to learn more and expand my understanding of the fields of physics and computation. I hope that answers it.
Okay. No, like how is it possible for a like computer student? They don't have computer physics background, right? Like linear algebra, quantum mechanics, that bracket notation, all these kind of stuff. It's not actually there in computer science. So how is it possible
Yes,
for a
I understand that concern, but you see, I think your degree should not hold you back. Because just because I'm studying computer science doesn't mean that I don't have access to the internet. Of course I do. And you have access to so many amazing mentors who can teach you. And I was a part of a research program this summer where I was able to be under the guidance of a couple of professors, Dr. Philip Barr from Oxford and Dr. Gerhard Hellstern. And these are people who are pioneers in the field of quantum computing. So really, I just think that despite the fact that I am a computer science undergraduate, if you're looking for the right information, you can find mentors who are willing to teach you, to help you grow, and really just expand what your understanding of a subject is. Plus, a lot of what you do in quantum computing, like for example, working with Python, understanding linear algebra, these are concepts that you do cover in computer science. And if you're worried about the physics aspect of it, honestly, just open YouTube. There's so much to find over there. And if you have access to the internet, there is nothing that you cannot find. So I don't think that's ever something you should worry about. If you have Wi-Fi, you have access to all the information in the world. I hope that answers it.
Okay, how did you approach all those professors and experts in this kind field, like quantum computing, as you have mentioned, Oxford? Uh,
Well, I was a part of a research program with Girls in Quantum and Thinking Beyond. And so we were actually assigned mentors, and that is where I met my mentors who I just mentioned.
so how to join the in this research? Is there
I
any?
would actually say, I would say, keep your eyes open, look on LinkedIn, and reach out to people who you think might be in the field, because it really helps to, I think, connect with other people and ask them, like, can you please guide me in the right direction? And they usually provide you with the links or the resources that you need. I mean, like for me, for example, I found the application for the program on LinkedIn. And that's where I joined. And then they had their interview process and everything. And then I passed. And then that's how that went on. So I would definitely say check social media platforms. There's so much to see. I hope that answers it.
Could I ask questions like in second? Uh,
Yeah,
like
yeah, sure.
yeah, okay, sure. For your background is in like computer science, so I would like to like ask about the benchmark on the days right now, like the OpenAI O3 models. Yeah, what do you think of it? Because like
I
this is
don't
about not just AI but AGI right now. Yeah.
Honestly, I don't really think I have much of an opinion on that. And I think that's, um, I don't look at things from that aspect. I'm looking at it more from a creator aspect, as in how can I expand what I know, as in by building neural networks of my own and looking at the work people have previously done. So I don't really have an answer to your question because I'm not that involved with kind of like current hype tech. I'm sorry, but yeah, if you have
Okay.
any other question, I would have an answer to that. Okay. Any other questions?
Is there any Python course available for computing?
Yes, yes, there's actually a lot of them. If
Like
you
online, is there any any particularly to join?
You know, the thing is, I've done so many courses by now that if you ask me a specific one, I don't really remember, so I can't tell you right now. But if you're really interested into checking that out, I'm assuming you have access to my LinkedIn profile. You can definitely check them out because I've done a lot of certifications in those. If anything catches your eye, please do check it out. I don't remember any right now because there's many of them.
Okay, thanks.
Yeah. Any other question?
Yeah, it was a great session, Roshni.
Thank you. Thank you so much. All right. If that is it, then I would like to conclude by saying thank you so much for joining. You guys were amazing participants, and I hope you have a great day and a happy new year. Have a great new year.
Yeah, Happy New
I'm
Year.
Thank you. Thank you. I hope you guys have been having an amazing holiday season, and I'm gonna see you guys next time. Yeah.
Hey, thank you
All
so
right.
much. Happy New Year.
Thank you.
Thank
Happy New Year.
Thank you. Thank you, you guys. Thank you. I'm ending the meeting
Like,
now. Bye.
okay, okay,
Yeah.
see. Could I
Okay.
ask,
Bye.
like, because
Yeah.
right now, like, technology is more advanced in many, like, disciplines, including, like, in medicals, in finance, in, like, many. So, like, what should the students or what should the investor, like, invest in what, like, fit the most right now? What do you think of it?
You know, honestly, I think from a student's perspective, the only thing that you can do is focus on learning more because one of the things like as a computer science student, it also scares me is that ChatGPT might as well take over my job, which I don't even have yet, by the way. Which I think is something we all think about a lot. But so my point is from a student's perspective, the best you can do is learn. Find the resources you have, find the people that you can find online. There's so many of them. You just need to keep a lookout for them. And once you find them, then it's great to get you need to learn. You need to learn as much as you can because right now we're not in the place to think from an investor's point of view or from a business point of view because you need to first know. You need to know the intricacies of what is quantum computing, for example. How do I create a Q-sharp program? And when you know such things, when you know the basic foundations, when you can do it yourself, that's when you put yourself in the shoes of the investor. And then you think, okay, will I be investing in this technology or that technology? Or how am I going to persuade other people to purchase the technology that I'm creating? I hope that answers it.
Okay, thank you very much again.
Okay, thank you so much. I'm going to be ending the meeting now. Thank you so much for joining, everybody.